So let's apply some of the relationships that we've derived. Let's say we have a mass of 5 kilograms, spring constant K equals 1,000 newtons per meter, oscillating with an amplitude of 10 centimeters. And we want to know what the velocity is when x is 4 centimeters and what the maximum velocity is. Okay? Now my recommendation here is that as soon as you see mass of 5 kilograms and spring constant 1,000 newtons per meter, you ask yourself, can I put those two together to get anything really, really important? And the answer is darn right. That's K and that's M. We get omega equals square root of K over M. Now, as I said in class every year, I tell people, the most fundamental thing you want to look for in solving most problems involving simple harmonic motion is this relationship, omega equals square root of K over M. If you know two of these quantities, you can find the third. So if you know omega and the spring constant, or the force constant, you can find the mass of the object. That's kind of an important thing, isn't it? Okay? And if you know the mass of the object and the force constant, of course, you can find the angular frequency, okay? The angular velocity of the point on the reference circle, which allows you to determine how long it takes to oscillate, how many times per second it oscillates, okay? And if you know M and omega, you can find the force constant, which is very useful, for example, in figuring out potential energies. Okay, well, we calculate omega and we get, I estimated 14.2 radians per second. Turns out it's 10 times the square root of 2, as we found out later, but I didn't think of that at this point. Of course, you know, 5 into 1,000 is 200, and the square root of 200 is 2 times the square root of 2 times 100, which is 10 times the square root of 2, okay? So I could have estimated that just a little more accurately. I was thinking it was going to round off to 14.2, so I feel pretty bad about that. Okay, well, so down here we get what? We get our x of t function. Okay, x of t is just your amplitude times the cosine of omega t plus phi. Now we don't know what phi is, and we're not going to address phi today. We'll come back to that in about a week. But we have this, okay? From this, we can take a derivative and get v of t, and we can take another derivative and get a of t in case we want to find those things, okay? What's the total energy? Okay, well, actually, let's go back here. Well, let's figure out what we can find out once we've got omega, and then knowing the amplitude, we can find all this stuff, including the total energy, 1/2 Ka squared, okay? And that's 5 joules. I wrote 50, watch me. We can also write the potential energy expression for potential energy at x. Remember, the potential energy is just the integral of your equal and opposite to the integral of your force function between 0 and x, and that's 1/2 Kx squared. Okay, remember that, but kind of remember where it came from too, in case you happen to forget it. You can always rederive it. Okay, so 1/2 Kx squared, well, there's K, there's 1/2, and you know, instead of 0.1 meter, you're going to put in x. Okay, instead of a, you put in x, and this is the expression you get. That's very straightforward. So now we know a lot about this oscillator, just from the mass, the spring constant, and the amplitude. We get all this. Okay, so now the question is, what's the velocity when x is 4 centimeters? Well, there are ways to get this. You could take this x of t and find the value of t when x is 4 centimeters, okay? And then you could plug that t in into v of t and find the velocity. That's feasible, especially if you happen to know what phi is. But we don't know what phi is. That complicates things a little bit. We can still get around it. We can still solve it. But it's much easier to use energy conservation. Well, you know, we know the total energy, which is the sum of potential and kinetic. We know the potential energy at a position. Well, if we know the total energy at all positions, the 5 joules, and we know or can calculate the potential energy at that point, then we can do a very simple arithmetic operation and get the kinetic energy. And once we have the kinetic energy, well, we know the mass, so we can easily find the velocity. Okay? Very simple if you remember and if you get used to thinking in terms of energy conservation. Okay? And this example will help you do that in a lot of different contexts. So, at x equals 4 centimeters, we can calculate the potential energy. Well, you can plug into this. We get 0.8 joules. It follows then that the kinetic energy is just the total energy minus the potential energy. Why is that? Well, because total energy is kinetic plus potential. Think about it. 0.5 joules minus 0.8 joules is 4.2 joules. Okay? Now, okay, well, got a mass of, what was it, 5 kilograms, 4.2 joules of kinetic energy. We can easily set 1/2 mv squared equal to the kinetic energy, and the only thing we don't know is V. So we can solve. In general, solving this equation for V, we get V is square root of 2 times the kinetic energy divided by m. Okay? And then we just plug in our 4.2 joules and our 5 kilograms and do a little arithmetic, and we end up, I estimate, around 1.27, 1.28 meters per second, something like that. Okay? Then the question is, what's the maximum velocity? Okay? Well, maximum velocity occurs when the kinetic energy is a maximum. And that's when the kinetic energy is the total energy. Where does that occur? Well, it occurs when the potential energy is 0. Okay, so if it's not obvious to you, be sure you think about why that is. And of course, the potential energy is 0 when x is 0, because here's your potential energy. The only way that's going to be 0 is if x is 0. Also, if you just think in terms of what potential energy is, reference point is 0. Where do you move to get a 0 integral between the, at what point do you get a 0 integral from the reference point to that point? Well, it would be 0. You go anywhere at all, and you're going to get a non-zero amount of work, because as soon as you get away from the origin, the negative kx is no longer 0. Okay, well, anyhow. Okay, well, you can then solve this for Vmax, okay? And it's the same solution, square root of 2 times the kinetic energy divided by the mass, but this time the kinetic energy is going to be the total energy, which is 5 joules, not 4.2 joules. When you do that, I finally realized you get the square root of 2 meters per second, which matches this. Well, okay, it doesn't match this, but it matches the amplitude, 10 centimeters. Yeah, if you take the derivative and get your velocity, you're going to get 10 centimeters times your 14.2 radians per second, which is going to give you 1.42 radians per second, okay? And actually, I guess I did that calculation right here. I think this is about when I realized that that should have been 1.414. Okay? So, we plug in here, set equal to the total energy, we get our maximum velocity, or we can say, okay, well, V, if you do the derivative, substitute your 10 centimeters, which is 0.1 meter, you get this 1.42 meters per second times the sine of, well, it's omega t plus phi. I didn't want to take time at that point in class to write that out. I might as well write it out now. Of course, I'm taking your time to write it out. So I'll kind of write fast. Okay, well, that occurs, that's maximized when the sine is equal to 1. Okay, so your maximum velocity is 1.42 meters per second, and that occurs actually this would be negative because your derivative up here is going to be negative. I'll say the maximum of the magnitude of Vmax occurs when the sign is plus or minus 1. Now it's a truer statement than it was. And at either of these, the magnitude of your Vmax is going to be 1.42 meters per second, and the reason for that should be pretty obvious. Now again, notice the equivalence between the result you get using the 1/2 kx squared, or 1/2 mv. The kinetic energy function, or the velocity function.